In this lesson and the next, we will be focusing on exponential models. And the first one is kind of where this exponential model comes from. So given a derivative dy dt equals k times y, then the general solution is, and I wanted to go through this with you because it is not intuitive where this comes from. So as a reminder, when we're solving these differential equations, we need to separate the variables. Notice the variable on the right is y. K is a constant, by the way. So we need to move that y to the left with division as we multiply both sides by dt. So I will have dy over y equals, I'm just going to leave the constant on the right, it doesn't matter, and having it in the numerator is easier to work with than the denominator, so k times dt. All right, and then we're going to integrate both sides. Well, the integral of 1 over y is the natural log absolute value of y. And here we just have a constant, so when we integrate a constant, we just multiply it by the variable. On the right, we're integrating with respect to t, and then our constant of integration plus c. Solving for y, in order to cancel the natural log, I'm going to use e. So basically, I'm taking each side, and e is becoming the base, and what was already there is becoming the exponent, or the power of e. So e and natural log cancel each other out, leaving me with y. And now I have e to the kt plus c power. So now we're going to be using our exponential rules backwards. Think about if we were adding the exponents, where did it come from? And it came from multiplication. So real quick, I want to remind you that if we have x squared times x cubed, in order to simplify that, we would add the exponents. It would become x to the 2 plus 3 power. So what we have right now is something like this, e to the something plus something power. And so what we're going to do is rewrite that in the multiplication form that it came from. So I have e to the k times t times e to the c power. Okay, but c is a constant, e is a number, so this whole piece right here is what I'm going to call a new constant. I'm going to call it a capital C, and I'm just going to multiply it in front of that e to the kt power. So the answer for that differential equation is y equals some number times e to the kt power. There's our exponential model. All right, running through each piece of that exponential model, y is the amount of time after t, c is the initial amount, value, quantity, k is the constant of proportionality, which is just a fancy way of saying it is some sort of number, and then t is the amount of time. And just as a reminder, if k is greater than 0, we have exponential growth. If k is less than 0, we have exponential decay. So if we have a negative exponent, it would flip it to the denominator, and we'd basically be dividing by that amount instead, which is why it will get smaller. Starting off with a differential equation, we're going to be solving. This is one of those examples where I do not love that y prime notation. So first thing I'm going to do is replace y prime with dy dx. And then it's much easier for me to see how I'm going to separate my variables. I'm going to multiply both sides by y, and I'm going to multiply both sides by dx. Integrating both sides. The integral of y is 1/2 y squared. We're integrating with respect to y, so we treat it just like we would if we were integrating an x. We only need that plus c on one side. I always put that with my x side. Integral of 5x is 5/2 x squared plus c. All right, now in this case, we do not have to solve for y. What we can do, however, is I notice both of my fractions have a denominator of 2. So what I could do to make this look a little prettier is multiply everything through by 2. So that would give me a y squared. This would give me a 5x squared. And some constant times 2 is still some constant. So that would stay as a c. This is as far as you need to go with simplifying a differential equation like this. All right, another differential equation, another prime notation. For whatever reason, your book puts that prime notation here. So I did put it in my examples just so I could have an opportunity to remind you every time we see it. We're going to change that to the dy dx so that it is much easier for us to see how we're going to be separating our variables. So what I notice is that I have two terms with an x, and I want my x terms on the same side. So I'm going to subtract that xy from both sides. And then what that does is gives me an opportunity to factor the x out. And now I can separate my variables. So I'm going to divide both sides by that 100 minus y, leaving me with x times dx on the right-hand side. All right, integrating both sides. Some of you might be able to kind of number sense this. Some of you might want u substitution on the side with y. So I'm going to write that off to the left this time. Let u equal 100 minus y. And then we get du equals negative dy. We don't have a negative, so we just multiply that on both sides. So replacing my denominator with u, pulling that negative out front. And then this time, unlike normal, we're going to integrate that x side right away. So we get a 1/2 x squared, and I'll put my plus c on the x side. All right, so integrating this is negative natural log absolute value of u. In order to save time, I'm going to go ahead and put that 100 minus y back in, equals 1/2 x squared plus c. All right, next step, taking care of that negative sign, we'll multiply both sides by -1. As a reminder, c is just a constant, so it doesn't really matter what we do to it. It's still some constant, so we don't have to change it when we multiply by another constant. Now we're going to take care of natural log, so raising both sides to e. We get e to the negative 1/2 x squared plus c power. Now what we're going to do is use that knowledge from that example that we went through on the vocab page. We've got an exponential to a power that is being added. So it came from multiplication. So I am not going to go through all of those steps again. I'm just going to say that e to the c power becomes some constant multiple c, and then I have e to the negative 1/2 x squared. In order to simplify this, I would add y to both sides and subtract that expression from 100. So I have y equals 100 minus c e to the negative 1/2 x squared power. And that's the solution for this differential equation. This differential equation is nice. It's only got one variable. It's already on the right side. So we're going to multiply both sides by that dt. And I'm going to change that square root to a 1/2 power. Integrating both sides, we get y equals, I'm going to leave that -3/4, and then I'm going to multiply by the reciprocal of my new power. So it'll be t to the 3/2 power when I add 1. So I'm going to multiply by 2/3. And of course, plus c. Simplifying a little bit, those 3's cancel, and 2/4 gives me a -1/2 t to the 3/2 power. This one had an initial condition, a 0.010, so I'm going to sub in 10 for y. Sub in 0 for t. And solve for c. Of course, 0 to any power is still 0, so we're left with 10 equals c. So our equation is y equals -1/2 t to the 3/2 power plus 10. All right, we do have one more example. I'm going to record that in a separate video just to make sure I don't go over the 15-minute limit. This has been really glitchy and there's been a lot of wait time. So at this point, it looks like I'm up to 20 minutes, but I'm sure this is probably only a 10-minute video. So one more video for today.